Okay, so I'll try once again. Let us see if I get somewhere stuck, then I'll call them. So this is the one which we have already done, right? So we try to modify this optimization problem which was here, and we try to scale it by uh, a quantity gamma tilde. So that one you can observe, like we have this scaling going on, and the main motive was to make it in such a way that we can use it in a computer program to optimize. So we are trying to make this optimization problem in a better way. So we, as we, if you recall, then last time what we were discussing was this optimization problem for the SVM was not the correct setting. So we are trying to make it in a correct way. So are you people aware of these optimization strategies? Okay, why? Okay, so this one also I think I had covered last time. So in this slide, what we are trying to do is we are trying to minimize the optimization problem. Here you can see right now it's maximize. So we want to convert it into a minimization setting. So you know that maximization, if you want to convert into minimization, it's nothing but just in case of this, you can flip the denominator and make it into the numerator. So the whole argument or the whole objective function will become minimization here, which is given. And if you also know that if you scale it by a factor or you square it, if you square the argument by 2, the solution of the optimization problem which you are getting over here and the solution which you will get from here will not be affected. So basically both the optimization problems are nearly same. So what we are trying to get here is to come up with an optimization setting which gives you easy way to solve it. So this is our way of solving it. So this is the optimization setup where we stopped last time in the last lecture. So here what we observe is that it's a quadratic minimization, and why we are saying it's a quadratic minimization is because you can see you have a square factor here, so it's a quadratic terms involved because modulus, L2 norm of theta is nothing but it's theta 1 square plus theta 2 square plus dot 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 whatever variables you have, right? So this is basically a quadratic minimization problem. Uh, just a second, I'll ask them that. Online people, are you able to hear me and the screen, is it visible to you?
Yes, sir.
Okay. So here, this is the subjected to constraint which we had also discussed last time. This constraint is important because this constraint allows all the samples to be correctly classified. So if you see, I have already discussed last time in this particular slide, if you remember, let me go back here. So this thing we discussed last time, right? This particular factor where we were trying to say that this ensures that all the data points are correctly classified and it will not allow any data to be lying within the boundary. Like you have this SVM boundary, we do not want the points to lie in these points in this boundary. So what it is trying to tell you is that all the points should be outside this boundary and there should be no points within this inside boundary. So this constraint is actually giving you that additional constraint onto the main objective function which you have, the L2 norm. So if you see this also, it's somewhere close to same story only. The only thing is now it is 1 here. So you can see now that what it is trying to tell is that whatever boundary that you will come to separate these points, let us say you have these points here, right? And there are some crosses here. So whatever boundary that you come up with, it should be at least, at least, uh, at least unit distance from here. So this is what this particular constraint is telling you, and this one is coming because we normalized it by gamma. If you remember last time we had gamma here, right? So this was the distance gamma last time. But now when you transform that objective function by doing multiple transformations like scaling and doing other transformations to come up with this optimization framework. Then you observe that this is 1, right? So this one is nothing but it's a distance, and you want to ensure that all the data points which you are trying to classify, they should not be within this boundary. So that's why this 1 is from the main boundary. So this is your main boundary and this is the margin. This is 1 and this is 1. So this is what this particular objective function is trying to, this constraint is trying to tell you. Okay. Okay, so what we were discussing is this is a quadratic minimization, and the constraints that are involved here, the constraints that you have here, they are all linear constraints. Okay, there is no quadratic constraint, so it's a linear constraint problem. It's a convex problem also, as you can see. This involves theta 1 square plus theta 2 square plus all this. So if you plot this particular curve, if you plot it for a single variable, let us say theta 1, then you know that, if this is, let us say, y, so you know y is equal to theta 1 square is something like this, right? So it's a convex curve, and the solution to this particular optimization problem, the solution to this is basically the solution to the support vector machine problem, which is, which is given over here. So in case, if you see, I told you last time also, in books you will see this particular part, you will not see from where it came. So this is the whole story. So whatever book you study, it will be only starting from here. So this is the point from where we have to actually start, and this is the point where, this particular problem is correctly presented, so that we can solve. Okay. Okay, so what happens is, normally if you go to Python or any programming, whichever you want to adopt for, like for example MATLAB. In MATLAB we have this software which is CVX. So this is basically used for solving these type of optimization problems. And in Python also we have, multiple uh, programming solvers. So you can use them to solve for this particular framework which we were telling you, the one which is here. So you can solve this. So what I am trying to show is that this particular optimization problem which is given over here actually can be, cast into this particular, optimization problem. So this is basically a standard optimization problem where you will have some u vector, you will have some matrix q, and you will be, you will try to minimize u for this particular, it's a generalized setting for the program solver, and subjected to these constraints. So this is linear constraint. So if you compare this one with the existing problem which we have over here, the one which I have presented, you can easily, contrast that u will be actually theta, and your q will be identity matrix, because u transpose u will be modulus u, right? The L2 norm of u. So you can compare it with the one which we came up with, and you can easily contrast that what will be the values of q, what will be the value of u, what will be the value of a, and what will be the value of c. So once you have that values, you can actually use the solvers which are present in Python to get to this optimal solution u star. So this is one way of solving it, using the existing libraries in Python or in CVX, which is available in MATLAB, but it is nowadays available in Python also. You can try it out. So this is one way of solving for the support vector machines. So whatever answer that u star will be, you will be getting, u star is nothing but theta star. So this is the optimal solution that you will get for your problem. So this is the one way, and the another way which I will tell you now is through, through mathematical way of solving it. So we will go into the details of this particular SVM, and let us see how we can gain some intuitions from doing a mathematical derivations for the support vector machine. Because in support vector machine, machine you know already, but what is support vector? So that support vector, the mystery of that support vector will, come into limelight when you will, solve it through your mathematics. So once you solve it through mathematics, then you will know what actually this support vector is and why we are, working on this support vector machine. So let us go and understand that. Okay, so one way of solving this particular problem which I have given over here is through use of Lagrangian functions. So I hope you know that. If you do not know, I have a preliminary slide for that to make you understand. But have you heard about this Lagrangians? Okay, some of you, but still no problem. I'll go into the a bit of mathematical details of it to make you understand what this is. So we will be using Lagrangian functions to solve for this particular optimization problem which is given. Okay. So let me go there. Before going here, let me give you this slide just to make you understand what this is. So basically, if you have a optimization problem written in this way, like if you want to minimize something, that is this fx, and subjected to these constraints. So if you see here, this is a generalized setting for any optimization problem. So you have to minimize some function fx, and you are trying to constrain that solution based on these constraint sets which are here, like gix greater than 0, hix is equal to 0. I hope you are aware of these type of conventions. You know this, what this is actually, like in your optimization course you must be seeing these things, right? So this is basically the constraint sets, right? So what you are trying to do is you are trying to constrain the solution which you will be getting from this fx. You want a minimization of that fx. You want x that minimizes fx, but you want that x to reside in this particular area which is bounded by this gix and hx. So if you have this equation of gix like this, like for example, it is g1x, this is g2x, then you have g3x, then you have hx, let us say. So basically, all these all these boundaries will be formed by these constraints, and you want this function, which is over here. You want that function to give you a minimum value, but that minimum value should lie in this particular area, which is formed by this constraint set. So this is basically a typical optimization problem, and we try to actually solve it using Lagrangians. So let us see how we will do that. So what happens is we try to solve this particular optimization problem which I have noted down earlier using Lagrangian. So Lagrangian is actually represented as x comma alpha comma beta, and what we do is we actually use the original function fx minus we use these alpha i's time the constraint gix which we were showing you in the last objective function, followed by minus times beta hjx. So this is the typical way of forming the Lagrangian using the optimization problem which I had shown you in the last slide. So here basically your alpha i's and beta j, sorry, they are basically called as the Lagrange multipliers, or they are also called as dual variables. We will come to know what this duality means, but these are the alphas and betas are the dual variables, okay? And x, the one which you are actually looking for, is the primal variable. So here x will be theta, and alpha and beta are the dual variables which we will be using temporarily to solve this particular optimization problem. So x is the primal variable, and note that there will be a constraint on these values alpha I. Alpha I has to be always greater than or equal to 0. You cannot have value less than 0. So it can be always greater than or equal to 0. That is the main constraint on alpha I. And on beta j, there is no constraint. So we do not want any constraints on beta j. This is mathematically proved. So we do not want to go into the details of this, but the only information which we want is your alpha I is always greater than 0. Your beta j has no constraint. It can go from negative to positive, whatever you want. Okay. So if the solution to this Lagrangian is, let us say, x star, alpha star, and beta star. So these are the solutions if you solve for the optimization problem. Then there will be some conditions that this solution has to satisfy in order to be the solution for this particular Lagrange function. Okay. You cannot get any arbitrary solutions. That solutions has to satisfy some constraints to be the solution of that objective function, which is Lagrange here, and which is the main objective function where you want to solve for. Okay. So if the solutions that you are getting are x star, alpha star, and beta star, then these are the four conditions which we will be calling as KKT conditions. So these are called as KKT conditions, or Karush-Tucker condition. So these are the conditions which this solution of the objective solution of this particular optimization has to satisfy. So what are these conditions? The first condition is that if you get X star, alpha star and beta star, if you take the derivative, this is basically nothing but it's the derivative with respect to X of the Lagrange function. So if you take the derivative of the Lagrange with respect to X, and if you put the values of X star, alpha star and beta star into it, its value should come out to be 0. So this is quite obvious because you are trying to minimize the objective function, and if you put the solution of that objective function here, it will give you 0 only, right? So because that is the minimum point which you are trying to achieve. So this is basically also called as stationarity condition. Okay. And the primal variables should be stationary. So what it is trying to tell you is that X star which you are trying to put here has to be stationary. So that is what this particular condition is. The second condition is that if you put the solution X star into the constraint GIX. So the GIX, if you remember, they are the constraints, right? And you had HX equal to 0, HJX. So basically, if you put the solution X star into these constraints, then what it should do is it should satisfy this equation only, the one which you already had. So if you put X star here, it should give you a value greater than 0. And if you have X star, if you put it in HJ, it will also give you equal to 0. So this is the original condition should not be violated even if you put the solution X star of that objective function here. So this is also called as primal feasibility. So it ensures that the constraints which you are putting on the objective function are satisfied when you got the solution X star from that main objective function. Okay, any doubts here? Are you getting the points? And the third one is alpha I star should be greater than 0. So it should not come as a surprise because I have already told you in the definition that the values, this alpha i's which are the primal variables, this has to be greater than 0. So whatever solutions that you will get for alpha star has to be also greater than 0. Otherwise there is no point in putting this constraint. So that's why we have alpha I greater than 0, which is just following the basic definition of the Lagrangian which we had started out with. So it is also called as dual feasibility. And what it is trying to say is that it requires, I don't know, we can move it or not. I will try to. So what it is trying to show you is that it's saying that your alpha I has to be greater than 0 and the constraint on the beta I star which you will get, there is no constraint on it. So it will still remain the same. The fourth condition is very important, which will actually help you in understanding why we are calling this particular algorithm as support vector machine. So this will help you out in understanding the reason. So this particular fourth equation will come again and again. So please try to understand this. So what it is trying to tell you is that if your alpha I star, if you multiply it with the GIX star, which is the again constraint. So if you multiply the constraint, if you put the value of X star in that constraint GIX, and if you multiply it with the alpha I star, which is again the solution, one of the solution of that Lagrangian, so both the results will come out to be 0. So what it says is it's basically a complementary slackness condition. We call it as a complementary slackness condition. What it tries to tell you is that if your alpha, so basically you have alpha I star GIX star equal to 0. So you want to make the product of these two equal to 0, and you know that alpha I star is always greater than or equal to 0, right? So what it says is if your alpha I star is 0, let us say if your alpha I star is 0, it satisfies this constraint also, the inequality constraint. So what this equation tells you is that if your alpha I star is equal to 0, then GIX need not be equal to 0 because multiplication of them will be again equal to 0. So there will be, GIX star can be anything. And the second way is if your GIX star is 0. If your GIX star is 0, then there is no point in putting alpha I equal to 0. It can be greater than 0 also because multiplication of that will be equal to 0. Are you getting this constraint? Okay. So this is basically called as complementary slackness condition. Keep this in mind because we will come back to it, I think 2-3 times to make you understand why this will result in support vectors in that support vector machine. Okay. So this is the only introduction that we wanted out for the from the mathematics part. So if we try to use Lagrangian for this particular object, yes. Third condition. Yeah, third condition is actually if you see this alpha star, this is already we are trying to use it in the definition of the Lagrangian. If you see here, what I am telling is alpha star has to be greater than 0, right? This is already we are putting it in the definition of the Lagrangian function. So if the solution that you get alpha star, that has to also be greater than or equal to 0, right? So it's coming from there. Okay. So most of the things are quite intuitive, except the fourth one, which is complementary slackness condition, and that actually helps you out in understanding further that how this will help us in getting it. Yeah. Can you speak loudly? See, this actually relates to the mathematical part, like how they derived this Lagrangian function. I don't want to go into the details of that. Otherwise, it will stretch out the lecture. So, what happens is they have come up with this alpha is greater than 0, as well as there is no constraint on beta based on the Lagrangian discussion that how they formed it to be a lower bound onto the function. So, I don't want to go into the details. Otherwise, it will move into the optimization area. So, what we wanted is like whatever minimum we can get from there and make you understand support vector machine. So I'm using it. So you can take it for granted that alpha star has to be greater than 0. If you want to go into the details, you can go for Stephen Boyd book on convex optimization. There you will get very easily understanding of why this is so. Okay. Okay. So this is the fun. This is the one which we want to solve using the Lagrangian functions. Okay. So this will be the Lagrangian function for the optimization framework which we have just shown you before. So if you compare this one with the Lagrangian function which I have shown you here, this one, this is exactly the same. You can try it yourself, you know, by forming the Lagrangian for this particular objective function, the one which we have posed earlier. So this is the main objective function, and this is the lambda j times the factor here. So somebody can ask what this lambda j is. Lambda j is nothing but it's actually replaced with alpha. So what we were saying alpha is now lambda. But if you recall, there is no h here. This is the optimization framework, right? So this is basically an inequality constraint, and this is nothing but it's a gx, right? And there is no hx because hx equal to 0 is not there. So hx, so the corresponding beta also will not be there with that because beta times hx. Hx is not there, only gx is there. So corresponding to the gx, we have alpha. So that's why we have alpha in this problem. But for my understanding, what I have done is I have replaced that alpha by lambda. So you keep this in mind whenever I will tell lambda. If I put some constraints on lambda means I am putting constraint on alpha. So basically lambda has to be greater than or equal to 0. This has to be kept in mind because I have replaced alpha by lambda. So keep this in mind. So the first thing that you will do once you have this Lagrangian is to take the derivative with respect to the primal variables theta and theta 0 and take the derivative with respect to lambda. So what you have to do is you have to do derivative with respect to theta, theta 0 and lambda, and you have to keep it equal to 0. This is coming from the first condition of KKT. If you see here, the first condition is to take the derivative of x, right, with respect to the whole thing. So what we are doing is we are actually using the derivatives here with respect to theta, theta 0 as well as with respect to lambda. So we are trying to find the solution because if you want to minimize some objective function, that will be done through taking the derivative, right? You do it right that way, right? Minima, if you want to calculate minima, you will take a derivative of that function. So this is what we are trying to do here. Okay, this solution will happen when both of them will be equal to 0, then you will say that this is the minimum point. Okay, so now if you see here, I am rewriting that Lagrangian function again. So what I am doing is, this is the one which is over here, and this is basically the objective function, sorry, the constraint that you have. So what we are trying to do is, earlier if you recall, we have yj theta at transpose xj plus theta 0 greater than equal to 1. So what I am doing is, I am taking 1 minus that side, so it will be less than 0. So what we are trying to do is, we are trying to write in this fashion. And you can recall that this particular thing will be always less than 0, because if you bring in this particular expression this side, so it will be 1 minus, so it's always less than 0. So this is the Lagrangian function. So now what we are trying to do is, we are trying to apply the complementary condition which we stated out earlier, and I was telling you it's a very important condition because it will help you understand what support vector is in support vector machine. So here what will be happening is, recall that this is alpha, but this is actually alpha, but I am replacing it by lambda. So if you see here, if your lambda is greater than 0, using the complementary condition which I have told you last time, if your lambda is greater than 0, we can make this equal to 0, right or not? Because alpha I star gi x star is equal to 0. So your alpha is, you are saying, is greater than 0, then your gi x star will be equal to 0. So this is coming from there. The other condition is that if your lambda j is equal to 0, then the corresponding gi x star can be anything. I told you last time, right? Because the product of two, lambda and g, is equal to 0. If your lambda is 0, then gi can be anything, right? So that's why you have this expression with the inequality. Okay, so this is basically helpful for us. I will come back again, but this will be actually helping us to pick up the support vectors concept. So keep this in mind. Okay, so what we are trying to do is, first of all, we will try to take the derivative with respect to lambda. We want to see whether we can solve this particular problem. So now what we are doing, we are trying to take the derivative with respect to lambda first. So this is basically the expression when you try to take derivative with respect to lambda for that Lagrangian function. So this is 0. Can anyone tell me why this is 0 here? Sorry? Right, good. So basically, if you recall, this is basically modulus theta square, right? So it is not dependent upon the lambda. So you are taking derivative with respect to lambda. So once you are taking derivative with respect to lambda, this thing goes away. It is 0 because it's a constant when you are taking derivative with respect to lambda. And now what you are doing, you are taking derivative with respect to lambda for this complete expression. So what we are trying to do is, we are trying to find the maximum or minimum of this, because you are taking derivative of something and you want to find the minimum of that expression. So we want to know whether we can get it from this expression by maximizing this expression or minimizing this expression. We want to check this first, because this particular expression, actually if you observe, we want to check whether this, what is the curve actually. We want to see which kind of curve it is, whether it's a convex curve or whether it's a straight line, what kind of curve it is. So if you see here, it is basically linear in case of lambda. If you observe, it's a linear in function lambda, because lambda is here, right? There is no square involved, so it's a linear function in lambda. So if you take this particular thing, and if you want to check how this particular curve looks like, then you know that this lambda j is nothing but it's a alpha. So we know the constraint that it has to be always greater than or equal to 0. So if we assume that it's greater than 0, then you know this particular expression also, it is always less than 0, right or not? Because this I have already explained. So you are multiplying a quantity which is greater than 0 with the quantity which is always less than 0. So obviously when you multiply the two, it will become negative only, right? So what happens is, this particular curve, first of all, it is linear with respect to lambda because there is no square term involved. So what happens is, the line is actually going down like this because of the negative value that you have. So it will always be going down, and what you want to find out is to maximize this argument, because there is no bound towards the lower side. You can go as much negative as you can in this particular case. So if anything goes like this continuously, you cannot find the minima of that, because it will continuously go down and down and down. The only way you can uh, find the stable point of this line, which is always going down and down and down, is to find the maximum value, maximum point. So that point is fixed actually, from where it starts and it goes down. So you cannot find the minima of this, you can only find the maxima of this. So what we do is we actually do something like this. We try to find the value of lambda star, which is the maximum value of this line. We want to find this lambda star, which is the maximum value of this line. And this is nothing but you are trying to find the argmax. You know this, what this argmax is? Anyone? You know this argmax? No. Okay, so argmax is nothing but what happens is when you apply argmax to the argument which is here inside. So what happens is if you write argmax here, it means nothing but it will try to find out the value of this argument. It will try to find out the value of this lambda which can minimize this argument. So if you write argmax something, it has to find out a value of lambda. Like you will have lambda 1, lambda 2, lambda 3, lambda 4. So there you will have multiple lambdas, right? So you have to put these values into this particular expression, and then you find out which one is the minimum lambda that can, which lambda can minimize this expression. So once that value you can find out, that value corresponds to lambda star, and that's why we call it as argmax. So argmax is trying to find out that. I'm sorry, not minimum here, it will be maximum, other way around. So you have to find the value of lambda which can maximize this argument which is inside. So whatever value of lambda which will maximize it is the lambda star. That's why we write argmax onto this expression. So once you find out this lambda star, what happens is you will put it into the original Lagrange equation which we already had. So we are trying to actually break up the optimization problem into two steps. In the first step, we will try to solve for lambda, and once the solution for the lambda comes, we will put it into the Lagrange again to get the solution for theta and theta 0. So because you can recall, what we have to do is, we have to take derivative for both. We have to take derivative for this, and we have to take derivative for this. Once we get the solution lambda star here, what we will do is we will put this lambda star here, and then we take the derivative with respect to theta and theta 0 to get the answer for the final solution. So this is what we are trying to achieve here. So once you have this lambda star, you can actually put it into this Lagrange here. And now once you put lambda star into this Lagrange function, you will see that all the values will be of theta and there will be no lambda star here. So the whole objective function will be involving theta. There will be no lambda, because lambda you have replaced it by lambda star value. So it will be like for example 2 or 3 or 4, whatever. So that thing is replacing. So everything is involving theta. Okay. So we are trying to actually solve for the optimal values of theta. Basically, once we get the optimal values of theta, you know, we will get the decision boundary, which is theta 0 plus theta 1x plus theta 2x, which we used to do earlier for case of linear regression and for classification. So basically, once you put that value lambda star here, what happens is, if you recall, we have this max here and we have this minimum here. So this max and this minimum will be actually combined together. So here what happens is you can push this theta inside. You can push this theta inside, because if you push max out, there will be no problem, because lambda doesn't affect theta. So theta is independent of lambda. You can move theta inside and you can push max outside. So if you do that, the expression will be like this. So this is not W0, this will be theta and theta 0. So what happens is, the problem which you were trying to solve by taking the derivative with respect to lambda and then putting it into the theta 0, it turns out to be a min-max problem. This is basically a min-max problem. So this problem is quite famous in computer science. So I don't know whether you have heard it or not, but it comes in the area of game theory, as well as if you go for generative adversarial networks in deep learning, you will find out that min-max in that area also. So this is min-max problem, and it's basically it's a little bit tough to solve it. So what we do is we try to try to solve it in another way. So let me show you that. So, so what, sorry. So there are basically, we want to solve for min-max situation. So what we will do is we will go to another space. So that space is called as dual space. This particular problem which we were solving is in primal space, because recall that theta and theta 0 were primal variables. So we were trying to solve for theta and theta 0 which are in primal space. You don't have to go into the details of what these spaces are. This is just for, for your understanding. If you want to go into the details, you can go yourself, but I'm not going into details of that theory here. But what we are saying is we will be going into a dual space, which I will try to make you understand what that is in a coming slide. But let me go there. So what we are trying to do is we are trying to actually solve for this problem, which is min-max problem, which we have seen. Maybe you will see later on when you will go for some other courses, that this min-max problem is a bit hard to solve, because there are two optimizations which you are doing simultaneously at the same time. You are maximizing also, you are minimizing also. So it's a bit hard. So what we try to do is, this is basically the primal space where you actually got a min-max thing, and what you want to do is you want to go to the dual space, which is nothing but max-min. So you reverse the things. So you, instead of min-max, if you do max-min, that is still hard, but the problem is it will help us in understanding support vector machines, because in this you cannot get any intuition that what we will be getting, what is the support vector. So here in this solution you will understand what this support vector is. But in this case, if you try to do the intuition, you will not get that what is the support vector in support vector machine. So we will go for this max min of the Lagrange function. And the problem is this equality. So the discussion is, can we actually replace min max with max min or not? That is the main question. So this equality can hold if you are solving a quadratic programming optimization framework. So you know that you are already solving for theta 1 square plus theta 2 square plus theta 3 square. So that is actually quadratic programming. So in quadratic programming, you can actually replace max min with min max with max min. But in case if it is not a quadratic programming, then what will happen is it is actually greater than or equal to 0. So in that case, it's tough to do it. But in case of quadratic programming, you can easily replace the first one with the second one. So again, we are back here. Now we are trying to do in dual space. Earlier was in case of primal space, now it's in dual space, and that can be seen from this. Earlier it was min max, but now it is max min. So we will actually first do the derivative with respect to theta and theta 0, and then we will substitute that values of theta and theta 0, which you will get into this value of lambda to get this solution for lambda. So that is why we are calling it as dual problem, because finally you are solving for lambda, and lambda is actually the dual variable. That's why we are saying we will go for the dual space. Okay. So so this is basically the objective function from where we initially started. And now this is the same Lagrangian function which you have, the original one. Please do not talk, whosoever is talking. Okay. So in the dual setting, what you are doing, you are actually doing max of lambda followed by minimization of theta. So the first stationarity condition of the KKT, which we have started out earlier, which is the derivative with respect to x, and I told you that this is nothing but theta and theta 0. So we are doing that derivative of the Lagrangian with respect to theta and theta 0. So if you take the derivative of the Lagrangian with respect to theta and theta 0, you will get this expression, and you will get this expression if you take with respect to theta 0. This you have to derive. I will not do it. It's your, call. You have to do it yourself. So this is basically the derivative with respect to theta and theta 0. And from this first equation, the one which you have here, if we focus on this first equation, what it is basically this. This is the first equation that we get when we solve for theta and theta 0. So there is an interesting observation from here. The interesting observation is that this theta actually will give you the answer for theta star and the optimal values of theta which you will be using for the hyperplane, right? So these are the optimal values of theta which you use for separating the boundaries, if you recall that. So that is actually, this theta is actually what this theta is. Theta is basically the summation running from 1 to m. M are the total number of samples in your data set. It is nothing but lambda times yj times xj. So what it is trying to show you is the value of theta that you get for that hyperplane is nothing but it's the summation of all the values of labels yj corresponding to that corresponding data point xj, and you are scaling it with lambda. So it is nothing but it is lambda 1 y1 x1 lambda 2 y2 x2. So you can see now all the data points, what you are doing is you are multiplying the labels corresponding to the data point and you are scaling it with lambda. This is what this equation is telling you, and this is the boundary actually, the boundary which you will get, and you know the definition of this boundary is nothing but theta 0 plus theta 1x plus theta 2x. So we are trying to find out these optimal values of theta, and they are basically obtained through this equation which is given over here. So it's a running summation. And the and the important point is that this lambda, if you recall this lambda is nothing but it's alpha in the initial start. And you know this is always greater than or equal to 0. So it can be 0 also and it can be greater than 0 also. So both the conditions can be possible for this theta. So what I am doing now is, once we get this theta value, I want to put back into the Lagrangian to get the solution for lambda, because I told you last time, right? We will solve for this theta. Once we get the solutions for this theta, we will put it back into this Lagrangian, and then this Lagrangian will have all the values lambda, all the values involving lambda, because you have substituted the value of theta back into this Lagrangian. So now you have to do is you have to maximize that lambda. So basically what we are trying to do is we are substituting the value of theta which we have obtained in the earlier slide. So here the answer is there, right, for the theta. So you are actually substituting that value here, and you are substituting the value of theta here. So once you substitute these values of theta, you will see everything will be involving lambda. Okay. So once you solve I will not go into the details of this, you have to solve it. So this is basically the simplification of the expressions with how you are solving it. So you have to do it yourself, this Lagrangian. Once you substitute the value of theta, you will get the expression for lambda. And the important point is this is the final expression. This is the final expression once you substitute the value of theta and theta 0 into the lambda. So here you can see everything is involving lambda. There is no theta and theta 0. And this basically is 0 this factor is 0 because of the stationarity condition which we had earlier. So if you recall here, we have this stationarity condition, this one. I am using this equation to substitute that value in the derivation to get the value equal to 0 over there. So once I substitute that value here, I will get this expression. So now what you have to do is you have to actually, now you have to maximize this with respect to lambda, because theta we have already done. Now we have to maximize with respect to lambda. So this is the dual problem in dual space. In dual space means it involves lambda. In the earlier space it involved primal space where we had theta. Now everything is in lambda. So this is your dual space. You want to solve for this and you will get the answer for that as lambda star. So if you solve for this particular dual problem, what will happen is you will get answer as lambda star, which is the solution for this. So if you get the solution as lambda star, you can actually substitute that value of lambda star in the expression for theta, which we had earlier derived. So if you recall our expression for theta, this is the expression for theta, right? So once we get the lambda star, we can substitute that value here to get the answer for theta star. So basically now we again come back to the complementary condition which we were discussing last time. So here you have a lambda j, which is again nothing but alpha star times this condition, which is the gx condition. So alpha times gx equal to 0, if you recall that. So here in this particular complementary condition, we wanted the product of these two to be equal to 0. We wanted the product of these two equal to 0. I am telling this so many times, so I think now you must be comfortable with this argument why we wanted the product of these two to be equal to 0. So now if this is greater than 0, recall that if this is greater than 0 and if you want the product to be equal to 0 means this has to be equal to 0. If this is equal to 0, what it means is all the points are actually lying on the boundary. So this is the hyperplane boundary, and the points which you are actually, the value of the lambda star for which it is greater than 0, that points will be actually lying on the boundary. And if your lambda is equal to 0, then this is basically the constraint that you have to have for gx. And in this case, what happens is, that all the points just a second. All the points which are actually correctly classified. So basically this is the condition which actually tells you that the points are correctly classified. So you recall this condition which I was telling you last time. Here it is 1 right now. Earlier it was gamma, if you recall. So this is basically the condition which tells you that points are correctly classified. Okay. So the corresponding points which are correctly classified, that will have a value of lambda equal to 0. Okay. So this is basically showing you the diagram for the support vector machine and the complete story that what it is trying to achieve. So this is the boundary which we are trying to get as the answer. This is the boundary, and the region, this one and this region. These are the points, like the blue points and the purple points which you want to separate. So these blue points and purple points you want to separate, and the class for these blue points is y equal to -1, and the class for the purple points is y equal to 1. So what happens is, from the equation that we have discussed, all these points which are correctly classified are governed by these equations, this one and this one. This you can recall from the optimization framework also, from where we started. Initially we told that all the product of yj times the result of the hypothesis function has to be greater than gamma. So that gamma was normalized and it is equal to 1 now. So basically this region and this region, they are already satisfying this equation. Note now that lambda is actually 0 for all these data points except the points which are here. These 2 points, lambda is actually greater than 0, but for other points, lambda is actually equal to 0. Here also and here also, the lambda points will be having greater than 0 value, and for all the other data points, this points and these points, your lambda will be greater than 0, and this is coming from these conditions. So you can see if it is lying on the boundary, then the lambda will be having greater than 0, and if it is correctly classified, and then the lambda will be equal to 0. So all these data points are correctly classified, so these data points will have all the values equal to 0 for lambda. But for these points, these points and these points, actually they are lying on the boundary of the separating hyperplane, because this is the main one and this is the margin one. So the equation of these lines, the equation of this line and the equation of this line is nothing but this equation. This is the equation of the line. So for this, it is theta transpose xj plus theta 0 equal to 1. For this, it is theta transpose xj plus theta 0 equal to minus 1. So the points are actually lying on this, satisfies this equation. So all the values of these points will be having lambda greater than 0. For all the other points, the value will be equal to 0. So that's why we call them as support vectors. Support vectors are coming because they are actually helping, these data points are actually helping in formulating this decision boundary which is over here. Because you can see it's a summation, right? So here if you see, theta star is nothing but lambda j star times yj xj. So here if you expand this, it is lambda 1 x1 y1 plus lambda 2 x2 y2 plus lambda 3 x3 y3, like this. So let us say most of the data points are, let us say all these values are 0. Lambda 1, lambda 2, lambda 3 till lambda 50, all the values are 0. That means what? That means correspondingly the x1, x2 till x50, all that data points are actually these data points and these data points. But for the values where lambda has some value, that means the corresponding data points xj and their corresponding yj will be actually these points which are lying on the boundary, this one. So that's why the values of lambda for which the some value is there, that is, they are acting as a support vector for this support vector machine. So that's why the name comes support vectors. So this is the story. So the advantage of this particular support vector machine compared to the earlier case of classification which we used to do is, if you have an extraneous point here, as I told you in the last lectures also, that if you have an extraneous point here, what will happen is that the decision boundary will change as because of this extraneous point, because this is far away from the data set. So your boundary will change because of that, because you are using L2 regularization. I did this in our earlier lectures. But in case of support vector, this will not be a problem, because what is happening is that this particular decision boundary is actually formulated based on these points and these points, let us say. So this particular decision boundary is formed based on these points, and these points are not affected because of this particular additional, extra element which is coming in the data set. So your boundary will remain fixed. It will not change, because this boundary is actually formulated because of these support vectors, and you are not adding something here. If noise changes these particular points, then obviously this decision boundary will change. But if you are adding something here as an extra point, the classification will create a problem. The boundary will change for the classification setting, whereas in this case it will not, because this is robust to noise. So this is the whole story for support vector machines. We still have lot of things to go for, but I think you people are, you have to take time to grasp this. I can understand because it involves lot of mathematics. So go home, understand this repeatedly, try to understand what's going on here.